that works. Cool.
I think you should unmute this and mute your laptop because you have the mic right. But
Okay. It's just the
microphone linked up to that laptop.
it should be, yeah.
So yourself.
Can you hear me, people? Yes, good. Okay, that settles it. Okay, so you set up. So you need to know how to go from one state to the transition probability of going from one state to the other state. In Metropolis Hastings, you set up a proposal distribution, right? So here, I'm just going to set up the proposal distribution to be a normal distribution. What that means is that if I'm near a point, if I'm near, if my current state is x, I want to know what is the probability of going to state x prime. So I centered I centered a Gaussian around my current state, and the probability and I sample for that from that Gaussian, and that Gaussian is easy to sample from, right? So you sample a point. Let's say, so this is a 1D distribution. I'm here. I have a Gaussian of some spread. Okay, I sample a Gaussian. It happens to be over there. And then I ask, should I go there? So that place, that new state in the original density, let's say I was at 0. And then I sample once and I jump to say there, say 3. Then that new state in the density that I want to sample has so much probability mass, or in the terminology that we've been using a lot this week, the energy is so much lower that I'm just going to go there, right? But if I go to another place with higher energy or lower probability density, then I flip a coin. I flip a bias coin. The bias of the coin is proportional to the difference between the probability, the ratio between the probability of those two states. So this is saying, if I jump to a state where the probability is higher than my current state, I always go there. But if the probability of the new state is lower than where I am, I go there. I will only go there sometimes. And how often do I go there depends on the difference between those two probability. Okay. I see some nods, and I'm not going to harp on this very simple algorithm. So this is just a description of, so just some terminology. There is a target distribution. This is the target distribution, where the distribution where you want to sample from. There's a proposal distribution. At every state, what state would you jump to? And then there is the acceptance rejection step, which is whether or not you want to accept the next state. Okay. So everything that it's coded up in. So this session should give you also give you a sense of algorithmic code complexity, not algorithmic complexity. That's the number of lines of Python you need to implement what I just said. Yes.
Is the acceptance projection thing happening on target or on the proposal distribution?
It's happening on the target, right? The simplified version is happening on target, but it's actually happening on both if you have sort of a asymmetric proposal. Yeah. Okay. Yeah. But the simple answer is it's happening on the target. Yeah. Yeah. It's the difference between the target, like are you climbing uphill or are you okay. Hill always means energy landscape, right? If you are if I'm going uphill, I want to drop down. Okay. All right. So let's run some example where I'm going to want to sample from a normal mixture with just 2 components. Okay. Let's see some examples. So let's say the mixture coefficient is 0.3. So one of the Gaussian is more important than the other one. Let me initialize. So just now I tell you how to go from one set to the other one. And where does that chain start? Okay, I'm going to just randomly initialize at 0. Okay, and the first one tells me to, okay, so my normal mixture, one of the normal component is centered around -2, another one is centered around 1. And the point here is that they are kind of close relative to the standard deviation I gave to both of them, right? Both they are within 2 sigma of each other. Okay, and I'm going to draw 10,000 is enough. Okay, let's do that. All right, that's 10,000 samples from this 1D example running on a single core M1. So quick, right? Okay. Sorry, this is not the first example I want. Okay, so there is also another parameter, which is your proposal distribution, the thing that allows you to jump from your current position. You can control how wide that is. So the wider the proposal distribution, the more you jump. So the more you explore this energy landscape, right? Let me put it as at 1.0 for now. Okay, and yeah, so this picture on the left-hand side here is a histogram of all the samples drawn. And then you can see that it fits the target distribution pretty well, right? This is the target distribution, one of them centered at -2 and one of them at 1. Right, okay. But, okay, so what happens if you don't sample a lot? If you only sample, say, 100 points, so if you only do this procedure until you have 100 samples in your pocket, not so good, right? The histogram doesn't line up with the distribution, which means that if you use these samples to compute distributional mean and just other things you want to compute from it, it's not going to be good, right? So you need a lot. So 100 is not even enough for this 1D case, right? This is 1D, right? 1 dimension. Okay, how's 1,000? Getting there, right? Just now I need to go up to 10,000 for it to be relatively convincing, right? Okay, so let's try the next one. What did I change for the next one? Okay, so the next one, I pull these two mixture further apart. Okay, right? Let's do that. Okay, right. So 10,000 is not so good anymore. And then I haven't explained what the right-hand plot is doing. The right-hand plot is kind of a diagnostic tool called a trace plot. It's nothing more than saying the x-axis is just the number of steps I have taken since I start the MCMC chain, right? So, and the vertical axis is just where I am, right, in this MCMC chain. So for example, at 0, I started. Right, at 0, I started here. I started at 0. Remember, I initialized at 0. I immediately jump to 4. So, right, so I jump here, right, and then I stay in the first few. Okay, let me zoom. Oh, that's really big. In the first few 100 steps, I stay within here. Stay within this regime of 2 to 4, and then suddenly. I fortuitously, before this, I don't even know that there are things on the other side, and I happen to jump there, and then I start to sample that side, and you can see this sudden jump to the other node. Okay, so multimodal distribution is known to be difficult for MCMC, all right? Okay, so if you see, so in a trace plot. So let's compare this to just now. This is kind of a healthy trace plot where there is where you have, it's like you are exploring in every chunk of your MCMC chain, you are exploring the entire space, right? Okay, So not saying that if you get something like this, you are unhealthy. This is you can if you know that your distribution is bimodal, then you can sort of say that, yeah, this is like if you just take each mode at themselves, slice up the 2 to 6, it's exploring that space. That's fine, right? And okay, any question for now?
Why are the sample the left-hand side and sample the right-hand side?
It's random. It's random. I can run again. It might change. Yeah. Okay. Exactly. That's exactly what I'm doing now, right? Okay. I'm just now my proposal. The standard deviation of the proposal Gaussian was 1. Let's now halve it so that before the distance between those two peaks, what was it? 4 to 2. So from 4 to -2 was 6. It was 6 standard deviation away. Now it is 12 standard deviation away from the perspective of how far I can jump, right? Okay, let's see that.
Do you kind of want to like propose a standard deviation to what you expect the standard deviation of the distribution to be or something like this?
Be careful though, right? Like the standard deviation of something that is big and then it need not match like the distance between them, right? Yeah. Okay, so okay, this is actually not what I was having in mind, but if I run it again, okay, there. Okay, so if you okay, let me not be okay. Let's keep at 10,000 sample and I just go all the way down to 0.1. Like it will just roll down one place, and then the chance of it exploring somewhere else is going to be minuscule, right? Okay. What are the cases? Okay, that was the 0.11. All right. So let's go back to 1. And now let's explore another kind of failure mode. Okay. So just now I initialize at 0.0. Let me initialize at -80. What that means is that I'm initialized like way out here, right? What do you think is going to happen? So it will be, let's imagine, let's be Metropolis Hastings for a moment. I'm at -80. Okay, my proposal distribution asks me to jump, let's say 1 standard deviation. That's still negative 79. It's minuscule differences, right? But the chance of I will take a step there. I'll take a long time before I'll always go in one direction, right? There's one direction where if I the ratio is always greater than 1. There's one direction where the place where I step is always going to let me roll down a hill, right? So you should expect something a trace plot that looks like. Okay, this is just complete failure. It's complete failure because I forgot to change this. Okay, I meant to put proposal 1.0. That's complete failure. This is complete failure where you step a while, you never reach the actual part of the distribution where the density is. And if this happens, this is really bad, right? This is you are thinking your distribution is somewhere where it is not. Okay, you had a question?
Oh, no, you're probably looking for it to have a burn-in, right?
Exactly. Yeah. I know some of you probably have.
Really wide, so you can find
Yeah.
it, but, you know.
So let me. Yeah. There you go. Right. I need to. Yeah. Okay. So this is where it will be stepping, like it starts from -50. It will always step in one direction until it hits this place. And then it starts sampling where it matters, right? So this is saying if you don't know where your probability masks are, and then you are randomly initialized anywhere, you probably need to chuck out sort of the first chunk of these, because those steps are not sampling. Those steps are just a Markov chain trying to reach equilibrium. Okay. Anyone have anyone who is expert in MCMC wants to think has some other failure mode? Yeah.
Technically, if I remember this right, technically you only get one sample by running the MCMC algorithm long enough. But what you do is you just run it one time and then you can like, you can thin it or, and you can pretend that you ran it multiple times by taking.
Yeah.
Samples from like far spaced out.
I think I had an example for that.
The end of your market chain.
Theoretically, I think that's. Yeah.
So I think if I do that and initialize at -2.
That would, yeah, that's completely untrackable.
Okay, so there's this other failure mode, right? So this is a target density. Okay, that might be too harsh. Okay, so there's this failure mode where if you look at successive steps, it is very correlated. If you are at one place in your distribution, and then there is just this big slope down there that you want to roll down, so you will just roll down for the next few steps. Once you reach the bottom, you will start doing the stochastic thing again, right? So this is saying that the stochastic steps, like the successive steps, are correlated, right? The MCMC distribution. Remember that we are looking for the long time behavior of MCMC, right? So a way to do that is to do thinning. So you will cull every 5 of them, so that you don't care about those samples that are correlated.
You mean you would keep every 5th one?
Keep every 5th one. Yeah, cull. Yeah, right. I think it's hard to demonstrate in this one, right? I need to find example where that actually make. But usually we do.
What was the standard deviation?
Yeah. Yeah, I mean, the auto correlation is already off the chart here. Yeah. Okay. Yeah, you can think a lot, and okay, I can think by 100. Yeah, then it means that so the complexity of MCMC is calculated in terms of compute per effective samples, right? So you even if your steps are really fast, but if your proposal distribution is not great, then you might need to take a lot of steps before you get one effective samples. So okay. Yeah.
On one of the examples where you had like pretty good bimodal distribution, and then it was spending time in one part of it and then spending time in the other, sort of flipping between the two. The measures, the usual measures of like Markov chain convergence, do they, yeah, if you do that for 10,000 samples or whatever, yeah, does those measures of Markov chain convergence, I can't quite remember what they are, but like
measures of convergence, I'm not remembering what those are either.
Like, I mean, when you run MCMC and use various packages and stuff, there are some quantities that are supposed to tell you like, did your change converge converge to the stationary distribution? Yeah. Can't remember what quantities they are. Yeah. We can talk about that later, but maybe this question becomes mute then. But I was just going to ask if like, you know, whether that sort of plot there, that trace plot would say, yes, it has converged because I've found two sort of regions of the posterior. Yeah. Or whether it's saying, oh no, I'm in different ones and therefore it hasn't converged. I don't know. So I don't know what those measures are. I would imagine it is not about knowing that you have converged to the measure that you want, because if you know what a measure is, you might just use that. I imagine that it is comparing whether or not it has kind of stabilized or something like that. So this is a diagnostic too. It's not, the trace plot is a diagnostic too. It's not saying that like either direction doesn't work. It's like if you have a healthy trace plot, it doesn't mean that it doesn't guarantee that you are correct. If you are correct, it doesn't mean that, for example, in December, it doesn't mean that you have a healthy trace plot. Yes.
Yeah, I imagine there are like statistics you can compute that compare the empirical variance of the samples you've generated so far to like the number of samples you need to take the MC of the Markov chain in order to have like an accuracy within epsilon or whatever of your true probability distribution, something like that, under the assumption that there aren't like these weird other modalities that you haven't sampled before.
Yeah. So, but yeah. So, yeah. Okay. I'm not an expert in MCMC health, but but I'll say that, as you can tell, this is kind of a hard problem, right? MCMC is a tool, and then use it with caution. Okay, it's kind of what I want to get through here. Okay, here's some eye candy for two dimensions. So if you are in 2 dimensions, you need a trace plot for every dimensions, right? Okay. All right. Okay. This is so if you can go to this link. It's by Chi Fen. I'm just going to steal his animation because it's so good. So this is an animation that explains various MCMC algorithm. So I want to get across that MH, metropolis hazing, is not what we use in practice. That's just kind of a tool for education. This is what we use. So this is metropolis hazing. So what so that circle there. So the center of that moving circle is the current position. That 2 circles sort of represent the Gaussian distribution centered around the current state. And the error is kind of is the proposed distribution proposing the next state, and it's green or red depending on whether or not it is accepting, right? As you can see, it is if the proposal is going up the probability density, then it will be more like it will just guarantee to be accepted. If it is pointing like away from this, it's called banana distribution. If it is pointing out into no man's land, it is not going to be one to step there, and it will just look at the next proposal. Okay, right. But there are lots of other ways to improve this proposal thing. Yeah. Yeah. So the question was, what was the 2 different circles? The 2 different circles was that's representing the proposal distribution, right? The Gaussian. Yeah, it's probably just drawing the 1 and 2 standard deviation of the proposal Gaussian, right? Okay, so there is something called HMC, Hamiltonian Monte Carlo. Let me slow that way down. Okay, so remember the 3 steps. Okay, 2 steps. You are where you are. You generate a proposal point, the next state that you want to go to, and then you run the accept reject thing. Okay, so this is another way to generate the proposed next step, which is with using the physics analogy, Hamiltonian, right? As we are all comfortable with that now, I hope. So you think of the likelihood landscape as your energy function, as a potential. If you want to roll down a hill, and then so in physics you have a potential, and then you set up a Hamiltonian system. It's a couple ODE. You want to solve this by solving this ODE. You are running physics, right? But to do that, you need an initial condition. So you need to start somewhere, and then you run physics starting from there, right? So, and the initial condition in physics, you need 2 things. 2 things define a state. Where you are, what's your momentum, right? So where you are is just where you are, right here. And the momentum you randomly draw from a Gaussian, right? So you randomly draw a momentum from a Gaussian, right? So maybe it would be better if I look at sorry. This is very fun. It's mesmerizing, right?
Some chance of accepting.
Yeah. So here's have 3 multi-model thing. So every time it is running this physics for a while. This is not gradient descent. I want to emphasize. This is not in gradient descent. Your task is go to the bottom. This is running physics, right? So in a simple harmonic oscillator, gradient descent just want to zoop. And but if you run physics just on the potential, so there's no friction, right? It will go do that, right? Okay, so this is running physics for a number of steps. And then where you end up, you would run the exact same accept reject step. This is where next proposed step. If it is downhill, I go. If it is uphill, I go with some probability. Okay, so the one, just there's many advantages of this. One advantage is that you are not relying on a huge step to go into the next well. You are relying on being pointing in the right direction and then having enough momentum to roll over to the next hill, right? Okay. Yeah. we are constraining our computer overload, yeah, with arbitrary animations pauses. Yeah. Yeah. Okay. All right. So and then the actual okay, go to this page and explore all the other things that people can do to sample from any distribution. I almost want to say posterior, right? So MCMC is not just for sampling for posterior; it's sampling any density. Oh, I should probably mention that and Hamiltonian Monte Carlo, it's great. One downside is that you actually need to your density needs to be differentiable. You are running some sort of gradient system here. You need to be able to differentiate.
Is it also computation heavy in the simulation?
So yes, the simulation each step is more computationally heavy, but computation per effective sample now goes down a lot, right? Okay, let me stop that before anyone get hypnotized.
In practice, you actually use a different one. You use the no Euclidean sample.
Yeah, I kind of want to not talk about that. So there is so in Hamiltonian Monte Carlo, you have hyperparameters of how many steps you take, how long do you physics this thing, and because this is a discrete system, you actually need to choose the discretization, and there is an algorithm that called the no Newton sampler that automatically tune that and also cut down on unnecessary research where you run your physics for too long. So imagine the well, if you run your physics for like 100,000 steps, you would do that, which is no different from run your physics for 100 steps and do that, right? So there is that no Newton sort of account for that and cut down the computational complexity. I think there are cool. All right, so we are going to use MCMC to do sampling from the posterior. So you have seen that we care about the posterior. Maybe some of you will object that we don't actually do Bayesian, but still, this is it's a density that tells us something about the model space, right? Tells us about the parameter space and how data concentrate. What part of the model space is more likely for the observed data, right? So okay, so I'm going to use I won't be able to code up Hamiltonian Monte Carlo in a few lines of Python, but there are tools out there that does it for you, right? So right, for example, you need to be able to differentiate your function, and then run if you want to do HMC or no Newton sampler, you need to code in your the physics part of this. And fortunately, we are in the era of deep learning where most code it's auto diffable, right? So JAX is a package where if you write functions in JAX, it will you can call grad on it, and then it will give you the gradient, similar to PyTorch, which yeah. So it's just one of those packages, and it will just-in-time compile and just-in-time compile it either to your CPU or to GPU if it detects it, or to TPU if you are rich. All right. Okay. Here, what did I do? Okay, here I'm going to I won't be, so there is some JAX, so there are some non-pyrocentric code idioms that you might need to familiarize, but preserving a little bit of my original goal that you can actually do this after this session, I would just say that it's not too hard. Just go to the getting started page of NumPyro and work on the example, and it won't be too hard, right?
You got the requirements. Requirement for TXC, some of these things.
Say that again.
Do you have requirements for these things?
Requirements, as in package requirements. Yes. Yes. Go to the repository. You can. Yeah, you can either use pipenv or you can use requirement.txt. Yeah. I literally asked ChatGPT that. So plate is the NumPyro and Pyro's idiom for saying that this bunch of this array you gave me actually consists of ID samples from the same distribution. Why is it called plate? I don't know. It might be related to how they visualize the graph of the dependency between a random variable where they draw where ID samples are drawn as plates stacked against each other. It's just their terminology. Yeah.
Oh, like.
Oh, someone know.
A plate of samples.
A plate of samples. It's more like a stack of plates is what they are. I don't know, like they can name however they want. There's probably significance to Pyro as well. Okay. All right. So here I'm just drawing from this model, which is one of the toy example in the talks, where this is just a one-dimensional linear regression. So you have a bunch of XY points, and then you want to find the gradient that goes through, so that the line goes through these points, right? And the XYs are related themselves by linear functions, but with noise, and the noise is a Gaussian noise. Okay, right. So you define the model in NumPyro like this. I'm just going to verbally say what that means. This means that I'm going to sample the parameter A, from a normal distribution. That means that I'm actually drawing A from a normally distributed prior. And then I'm going to use A to compute A times X. Just ignore the fact that I'm taking a power. K is 1 at the moment. And then the relationship between Y and everything else is given by Y equal to AX, and so Y minus AX is normally distributed. This is what that means. Okay. All right. So let's say, for example, the true parameter, the true line has gradient 1. K is 1. Okay. So here I'm actually asking NumPyro to sample multiple chains, run multiple MCMC chain. So each of these progress bar is one chain, and each chain here has 2,500 steps, except I'm going to throw out the first 500. That's the warm up part. Okay, and there's four of them. So in total there's 2,000 times 4, 8,000 samples here. I can also ask it to thin. So let's say thinning by 4. So now each chain is 2,500, 500 burn in, so 2,000 divided by 4, 500. Right, so it's 500 effective sample per chain. Okay, so and then that forms my that's my posterior sample. This is how you sample from a posterior. Okay, all right. So the true mean was there, and I am within 0.01 of the true mean based on this scale. Right, really good. Okay, so now just for fun, let's change the let's do different ends first. Let's say you only draw one sample.
Yeah, that wasn't that good, right? Because the standard deviation it was good, but like.
Right. So, but the standard deviation is small, so the mean is small, and if the standard deviation is huge, it means that actually, so like if the standard deviation is huge, it means that a lot of samples here are wrong, right? This is actually, it's the bias is small, the variance is also relatively good. This is 1,000 samples to learn a one parameter, so it should be good, right? So now if I draw only one sample, okay. Oh, it's pretty good. The bias is pretty good in this case. It's just, but you can see the variance is actually, this is a worse thing than last time because it goes up to 1.8. Just now it goes out to 1.02. Okay. So even though the mean prediction is really good.
The mean is less.
Yeah, cool, right. Scales, right. Okay. You have a question? Oh, sorry. All right. You have a question?
Sorry, I missed what this N represents because you still like draw, it's not the number of samples you draw from the,
Oh,
chain.
N is
it's like the data set size.
data set size. So
that
you
you're doing regression on.
yeah, you get 100 XY points,
Uh-huh.
and then you're doing regression on that.
Uh-huh.
Yes.
So what happened here? Because this plot is has got a larger variance.
Yep. Because I only gave it 1 point.
Okay.
So
I see.
right, one XY point.
So you
There's
would
like
expect-
tons of different
Yeah.
lines that go through that satisfy, that fits the constraint.
Thanks.
Okay. Right. Let's now do singular models. So when I said k equal to 2, it means that my model is now y equal to a square x plus eta plus noise. So what does that mean? It means that my KL divergence, that k of w function is k as a function of a, the parameter, is equal to a to the 4 now. So that's a singular, that's a degenerate singularity. And let's see what you have seen this in this plot. I'm using the same code. Let's 100 samples. Yeah, right. Okay, that was very dramatic because the A true is actually far away. So let me okay.
Should still work.
Yeah. A true is the true A, the A from which you generate data from, right? So you draw a bunch of X, multiply it by A true, that's your Y, and those X and Y's are your data.
In this case, you multiply it by a true squared.
Yes,
Yeah,
that's true.
and that's why you get two modes because suddenly the negative version of the gradient, when that's squared, also becomes the same. So that's why you get two.
Correct. This is now a non-identifiable model in which negative A and A encode the same model. Yeah. And that degeneracy, this is kind of literally a sort of a catastrophe of two things. So when A true is going close to 0 and your A needs to sample closer and closer to 0, you are previously you have 2 mode and then you are collapsing down to 1. Okay. Right. So this is not actually a dramatic one, even though the Gaussian is still struggling even at n equal to 100. Let's go to 1,000, say. Yeah, right. That's a right.
So can you explain what happened there? So you sampled 1,000 points from the line 0 squared times x plus noise.
Yep.
And so you would expect to have gotten Gaussian. And so what's happened instead?
Yeah, so the posterior looks like, so the posterior is e to the negative n ln w, and it's let's look at the mean. Previously it was n negative nw square. That comes from the fact that we are on a quadratic well, and that is just a Gaussian, right? Hopefully everyone recognize it as a Gaussian. Now we don't have a Gaussian, we have w to the 4. It's kind of a, it's okay. What does w to the 4 means? It means that if it drops off much faster than Gaussian, so that's why it's like the cutoff to 0 is very, very, very steep there, right? If you are away from 0, your w to the 4 increase much faster than w square. But near 0, it decreased to 0 also faster. There's more volume around there. So the volume where w square less than epsilon is less than the volume where w to the 4 is less than epsilon. Did I get it right? Yeah. Okay. There's more A that approximate the A-truths model up to epsilon. I am so running out of time. Okay, sorry. Okay, so this is another two-dimensional singular model. Okay, eye candy, not very important. Now I want to introduce something that would, I have literally a to-do set here, say something to satisfy the rationalists. This is about temper posterior. So this is a situation where you don't, I didn't write this out, but sorry to the people, but you can Google temper posterior. So usually your posterior is proportional to, so PW given a bunch of data is proportional to each, if it is RID data, you look at what that model says about that data, and then you product it, and then look at, and then multiply that by the prior, right? And then there's normalization constant. Temper posterior is you raise the contribution to the likelihood of each data point to a beta, and we call beta the inverse temperature. Okay. Concretely, what that means is that, so okay, now I have a inverse temperature I temp, like I temp equal to 1, you get back the same model. Okay, let's look at what's the effect if I go I temp, sorry, here's that value. Sorry, I didn't, if you want to follow along, here's that value. If you go I temp equal to, okay, I temp equal to 1 is you just get the same thing. Okay, you just get the same posterior, but inverse temperature equal to a huge number. So look at that that expression. If beta is a huge number, then you are saying that the likelihood part, so there's a likelihood part and the prior part. The likelihood part is very important compared to the prior. I don't care about the prior, right? Which means that it's like you observe one data point, you immediately update to the best fit parameter that fit that data point. Okay. So what this means is that right, you jump very fast. Okay, but if item is very small, then so if you are raising something to in the limit as beta goes to 0, the entire likelihood term goes away. Your posterior is just equal to the prior. Your posterior is equal to the prior. So that is a true. That is a true parameter. It should have concentrate there, but it is equal to the prior because the prior is I chose the prior to be normal 0, 1. So it's just equal to the prior in that case. Okay, this is temper posterior. Why do we want to do that? Because you can say that this is just a theoretical tool to perturb the posterior to gauge its response, so that you can derive, for example, the RLCT we're going to do next is going to be derived from how does this perturbed posterior changes, right? Okay.
Beta 1, inverse temperature 1 is normal Bayesian update.
Yeah, beta equal to 1 is normal Bayesian update, right? So just okay, let me actually say something to satisfy people who want to defend the Bayesian posterior. Your sample might not be ID. Then you don't want to trust each update to its fullest, for example, right? That's all I'm going to say. Anyone want to? Okay, all right. Okay, let's now jump to the next part. Now we know everything. I'll assume that we know everything about sampling from posterior. Yes.
Actually, I have a question related to that. Would that be like exactly the same as effective sample size when you have like correlated MCMC sample? So if you're not trusting it as much, you're like downgrading all of them.
Yeah, kind of. I don't want to claim any mathematical connection, but
I'm not saying,
yeah.
I'm saying it's like that on the surface. That's
yeah, on the surface level, you can think of beta times n as effective sample size.
And when beta is larger, like
You're
discounting it.
you're kind of discounting the prior kind of thing. Yeah, like let me ignore my prior.
when beta is higher.
When beta is higher, you're discounting prior, you are giving more weight to your data. Yeah. Okay. Okay. So okay. Really brief theory. Okay. So there is this paper by Watanabe, which might be the most widely cited ones because of how useful it is. It's called Widely Applicable Bayesian Information Criterion, or WBIC. So I think a lot of us know the BIC, which is Bayesian Information Criterion, which only holds in the regular case. And widely applicable WBIC is a correction to that holds for singular case, but you need more compute. You need to throw more compute at it to calculate its values. Some that there are I've seen people call WBIC Watanabe application Bayesian information criterion. It's not untrue. Okay. So there are various theorems in this paper that derive the things you can calculate from MCMC that allows you to estimate the free energy, for example. Okay, so the main theorem that is that, hope that is, okay, the main theorem that is that, okay, so that ln, if you remember, was the log likelihood, and ln is just is just a likelihood, right? Because in the energy function you actually average out. Okay, so just think of it as an energy function, right? So if you take the expectation E sub W, so this is a posterior averaging, and this is not the posterior, it is the posterior at beta. Okay, so you do that. So that's your posterior, that's your tempered posterior at inverse temperature beta. If you calculate that, and then you chose beta to be say 1 log n, so some constant beta naught, so just 1 log n, then asymptotically this quantity you calculate is related to the free energy expansion. So if you remember, the free energy formula has this term plus lambda log n. So lambda log n, so beta is log n, so there is a lambda log n on beta naught here, right? Plus some other things. Un is actually a random variable. So again, this whole thing is a stochastic quantity because this whole thing still depends on data. Draw different data, you get a different quantity for everything here. Right, so Un is accounting for that. Okay, so just quickly, the upshot is that, right, you have this formula. You have this formula. If you pick 2 betas, you get another such formula. I'm just going to write it with apology to people. Okay, so you pick beta 1 is equal to you can pick, say, 1 on log n. Say pick beta 2 is equal to 1.5 on log n. Okay, so E of beta 1, so beta I, both of them, n ln of W is equal to something that is the same for both, that doesn't depend on beta, something that is proportional to inverse beta. So beta is inverse temperature, so this is just temperature.
It's beta I.
Thank you. Plus lambda onto beta I, plus something that is even lower order term. Actually, Watanabe proved that this converges to a Gaussian variable with variance at most 1. Okay, so you have 2 of those. Think of what happens when you do minus beta 2. Okay, you take this 2 expression, take the difference. What do you get? Like the first term doesn't depend on beta, that cancel. You get lambda on 1 on beta 1 minus 1 on beta 2 plus, okay, those U's are random variables, so you need to draw them twice. So there is a root lambda on 2 U and first draw minus what did I miss? Oh, there's root beta 1 minus UN2 root beta 2. Okay, so these are different difference of Gaussian, and beta 1 and beta 2. So this quantity is so this whole thing here is all the root log n, right? So beta there's a log n in here and there's a square root, right? It's lower order terms than that. Okay, so if you divide by this term, which is all the log n, so this is equal to 1 log n. This is equal to 1.5 log n. You factor out the log n. Right? Okay, so if you compute this quantity, which you can do by MCMC, divided by this thing that you arbitrarily chose, and divided by log n. So this is root log n divided by log n is, if you take the ratio of this with log n, you get something that is decaying n, right? So this term becomes something that goes to 0, and this term becomes just lambda. Okay, I think I can just flush that. Yeah, so this, I'm talking about this formula here. Okay, so you can estimate lambda like that. Actually, you can do better. If you can do, you can do it for multiple betas, lots and lots of data, so that you can see whether or not this thing is noisy. So you can do a regression of beta against the expectation there. Okay, right. I'm going to just flash through everything. So this is okay. This is a 1-layer 10H network. So it's a neural network where the nodes there's only one hidden layer, and the activation function is 10H. Right, and the reason we are doing this is because we actually have a formula for the RLCT, which Watanabe and Aoyagi got calculated. Right. Okay, so this is just defining the network. I chose okay, let me choose a parameter. Okay, this is a singular model, but I'm choosing a parameter in which the Fisher information matrix is not degenerate here. Okay, it's kind of an important distinction. So this is a, okay, you need to trust me that the Fisher information matrix is degenerate near the axes. Okay, so if I choose this parameter, then this is the function is 1 10H, so this is just 10H of x, right? 10H looks like that. Okay, I run MCMC on that to draw from the posterior. Now I have a bunch of posterior point, which means that I can now do anything I can that does posterior averaging. For example, I can do the Bayes predictive distribution, right? That's the blue line. So if you give me a new x, if you ask me what is the y, I will ask its opinion on I'll ask the opinion of every model in my model. What's their opinion on what the possible y's are, and then I average them, but weight their contribution by the posterior, right? That gives me a pretty good. So the true function is actually the red one, and the blue is on top of it, right? And the spread there is the Bayesian uncertainty at each point. All right, and that is the posterior sample. Okay, this is actually a pretty large n. So you can see that the posterior concentrate near the true parameter there. That's the 1, and then because this is symmetric. But if I drop, I'm sorry, I'm going up and down. But if I drop it only to 10 data points, do the posterior sampling again. Okay. So this is a posterior sample. Now it's more spread out, right? And before, when it is so concentrated, it is actually very close to Gaussian. This is a bit further away from Gaussian. It's like there's no ellipse that you can draw that has bent, right? Okay. If you lower it more, then it will be more bent. Or if you if you bring the true parameter closer to where things are singular, let's say 0.5, 0.5, closer to the axes. So this is your new function now. It's closer to being flat, more bent, right? Okay. Red X is the true parameter, right? Now I'm closer to the axes, the red dotted axes are actually where the Fisher information matrix is degenerate, right? Here is close to degenerate. One of the eigenvalues is very small. Okay, right. Okay. Okay. In the interest of time, I think we ended sort of like 10 minutes ago. I apologize. In the interest of time, I'm just going to say that you can do this procedure for, say, here I'm being a bit wasteful. I'm doing 10 different betas here. All concentrate near where the WBIC paper says that if you n is large enough, then you will get lambda, get the RLCT, and then you do a lot of them. So these are all the temporal posterior. Okay, let me actually correct the other slides. These posterior are the ones where I chose them to be. I think I chose them to be at 0, 0, so that it's on the singular set. Okay, so this is a singular distribution. There's no Gaussian approximation to this ever, right? Okay, and if you change the temperature, you will get slightly different posterior sample that sort of that is probing the volume near it's kind of probing the density of states near W0. Okay, and then you do a regression against those points, and you get the slope is your lambda. This is a really bad ones, but okay, this is the last thing I do. So I'm going to do one where it is successful, and I'm going to tell you why it is not successful at that time. So I'm going to go back up to 1, 1, right? Far away, relatively far away from. Okay, this is my. That's what the posterior look like. Sorry, I need to go away from 1, 1, and I need the number of data points to be like huge. Okay, that. Okay, while all that run, I'm going to just say the upshot, which is there is a difference between your model being singular and the true parameter being singular for that model, right? You could have a singular model, but but the thing that you're trying to learn, the thing that's generating data set is actually a parameter point where the Fisher information matrix is not degenerate. Okay, that doesn't mean that your okay, if your Fisher information matrix is not degenerate, you actually do have Laplace approximation, you do have quadratic approximation. Regular theory goes through in that locality. Sure, it is not, it has a symmetry somewhere else, but in that locality, you have a quadratic approximation. So it's actually D on 2. So I'm expecting the RLCT here to be D on 2, which is D is 2. So the RLCT is 1. Yeah, RLCT is 1 here.
Singularities correspond to like the more generalizing function.
That is a very complicated story related to phases and phase transitions, right? For over-parameterized model relative to your sample size, that is kind of a complicated story, right? But yeah. The point is that you like in singular model that the singularities still have this reach outside that makes your convergence very slow. Okay, so here, okay, tons of temporal posterior, and voila, it's that being 1. Okay, I'm really sorry to go so much over time. There is another notebook that you can play that does the toy model superposition, and then you can go to you can go to the toy, like my GitHub.io toy models to look at what the result of that is in. Now you can do MCMC, right? And then you can apply that to a toy model. That's the upshot.
Thanks very much, Edmund.
I'm sorry for people online. I didn't notice this is not recording. Okay. Okay. Any questions? I hope the point is that you get sort of a sense of the code needed, code complexity, and compute needed to estimate things. So obviously I haven't shown you like more higher dimensional model. This is like I'm working in 1 and 2D here, but the toy models are actually you can go up to 20 dimensions, for example. Yes.
Oh yeah, well that's related to what I was going to ask, which is what's the largest number of parameters where you've been able to?
It's not just parameters, right? Because it's also a number of data points, right? Because you need to you need to evaluate your likelihood on the entire set of data points. So on these computers, I can probably do something like okay, what was that? 15 dimensional model on say 10,000 data points in hours, where I'm using all cores, like 6 cores, something like that.
So, so that's, and you can then do the RLCT regression on that.
With the caveat that I have no idea. So with all the caveat in the first Jupyter notebook, right? I have no idea whether or not that converge already or not. I have in the other independent checks of the things that I'm computing. So like the theoretical check that the RLCT is close to where I expect them to be, and so on, right? So maybe to actually get to convergence, I need a ton more, right? And I haven't said something. So you might despair that okay, this is really good for actually just studying singular model, period. But for deep learning, you need to be creative and you need to lower your standards of you're not going to get the RLCT, but you might get proxy of things that is ordered like RLCT, for example. Maybe the difference between RLCT is much easier to detect than getting the precise value of RLCT itself. And you need to do much more imprecise sampling methods, like for example SGLD or localized SGLD, where you don't care about other modes and you just care about the real locality and stuff like that. Yeah. Question.
You know, if there are, I mean, if we have a very big model, can you put your own numbers in there and be like, I am at this singularity and I can analyze the RLCT at that singularity? That's
kind of precisely what these analysis is doing, right? Okay. So we are using say, let's say we're doing a tiny toy 10H network. So you're saying I'm going to use this model. I'm going to be agnostic of what I'm going to use this model to learn. Could be learning MNIST, learning binary classification. I don't know, but I want to understand the behavior of this model at each possible parameter space, right? And SLT would tell you that you don't need to do that for every parameter space. You need to do it for there's a stratification, right? There is the regular point, the points where Fisher information matrix is not 0. There is close to a singularity, and there is kind of an ordering of singularity where the most tame one, the one that doesn't affect its neighborhood very much, speaking really loosely here, that doesn't affect its neighborhood very much, has the highest RLCT, and then you can go down that chain, right?
I was thinking more like generally, I give you a network. I also give you some loss. And then you can modify the network however you want. I don't care about what I get on the loss. What I care about is that you get inside of any singularity, which makes this easy to evaluate.
Oh, this need not be easy to evaluate. This algorithm is agnostic to whether or not you are on a singularity or away.
but you could choose which singularity that you're on so that it's easy to evaluate. Or like
So
can
that you don't
choose your
need-
position.
Yeah, so that you can, for example, you can constrain your prior to where you want to,
Mhm.
to where you want to study, and then your posterior would just be samples from that neighborhood. Yes.
Yeah.
That is actually a technique that we use. Yeah. Okay, I'm going to release everyone, and anyone who has, anyone who has a further question come. I'm saying.
Thanks, Hannon.
Yeah. Yeah.
What's the deal with SGL?
Oh,
What?
Dan is very bullish on that idea. I'm not so much. I do think that it is, it will eventually lead to somewhere. So the idea is that okay, again, like it's like we really don't care about the entire posterior.
Yep.
We care about where it concentrates and what is the characteristic with that.
Yep.
Right. So you SGD to that to there. So or you just jump there, right? Because I'm looking at here. So you run SGLD, which is just SGD steps, but every so often you inject Gaussian noise to your step. So you can think of it as like sort of bouncing around in that region, and you treat those bounces as samples.
Yeah.
Yeah. And you can compute, do the same thing. You can run the same equations where you pretend that the samples you get are from the posterior, and then you get something, not the RLCT, but it might behave in some way like the RLCT.
How efficient is that? Like what is that?
Oh, so SGLD is proposed because it is efficient.
No, but how many?
Don't know.
You know that.
Don't know. Right. So there.
What's the ones you've tried, I guess? What's the sizes you've tried?
Oh, right. For network size.
Yeah.
That thing can do that. So that is just that is just the cost of that is just SGD, right? That is very scalable.
So you
Yeah.
could scale that to a million parameter.
You can do that for GPT-4 if you are OpenAI, right?
Okay.
Yeah, you can do this for GPT-4 even if you are OpenAI. Yeah, right.
So then questions.
Yeah.
You can do what?
That's a bit facetious. So SGLD, which is, do you know?
I've heard of it.
Right. Okay. So SGLD is a way to get samples, not necessarily from the posterior, but samples in some neighborhood, right?
It's a variational technique.
Not quite. It's not a very it's not a very short. It comes from the theory that if you if in GLD on a very simple, say that like a quadratic well, if you take a random gradient step but inject Gaussian noise, you will eventually sample everything, and you can prove that with some condition that equilibrium distribution, so the tau samples is sample from the posterior with some heavy duty assumptions, right? Which is not true in singular models, right? So what we're saying is that, okay, that is just one way to get samples. What if we just try that and compute, assuming that we are taking things from the posterior, maybe those things have properties, they are not RLCT, but maybe they have properties that have, say, catastrophe flags, something like that, right? Like if things are sharply changing, it doesn't matter if your approximation is not good. The not good approximation will also sharply change, maybe. Yeah.
So with the RLCT estimation in the SGLD,
Yeah.
you still have to vary over beta.
Yeah. So there is a, if you want to be even cheaper. Yeah.
Your alpha weight space is
temperatures.
regular.
And then you did little
Unless you can go
yeah,
up.
yeah, yeah.
Yeah.
and then you just rearrange the
all that
equation
weight space.
to get the RLC.
And then once you cross into theta, and theta could be zero, you can,
You run,
I guess what
uh,
will help with
SGD,
the,
you just run SGD and you model this as like gradient descent plus noise. And you
know,
take, as the steps go to
the
infinity,
loss at alpha
this is
and
just
beta,
like the Gibbs.
or like
picture.
the loss at
Yeah.
alpha and beta, then. you
Okay,
should be
so the
able to
only
estimate
question is if
the,
T is not infinity,
delta lambda from alpha to
uh,
beta. And then if
then
alpha
what's
is
the
like
difference?
regular,
Like,
then.
like,
you should
as
be
in
able to
the
estimate
the open question is that
RLCT of your
if-
zeta or beta.
T is,
even showing that maybe you're on level set.
no, I was just trying to say like there's like, it seems like there's an open question with SGD and SLT, and I'm just trying to probe where it is, because it sounds like at the T was in, the T is because infinity is not.
Gap between SGD plus Gaussian is GD plus Gaussian.
But that's a pretty simple.
GD plus Gaussian.
You can deal with that.
Yeah.
Maybe you could deal with it, and maybe it's not the only thing, but it might be that. So it's just the outline.
Yeah.
So it's the difference between SGD.
Easier problem than analyzing the tricky scenario.
The difference between SGD.
Okay, well, that seems like a very small gap. I thought it was something else. Yeah.
We expect, like,
You
can always talk about, like,
yeah.
you can always draw a circle in
Right.
white space and another circle, they always something here.
Yeah.
I mean, technically, it doesn't apply.
No, I don't think it's conceptual.
Yeah.
I think it's
At least it seems like.
conceptual, but there's
Yeah.
information in there.
I mean, this is.
If you just do any,
Speculate. One line inductive bias is side.
Yeah.
RLCP as percentage corresponds to a similar model.
Like the inductive bias based on your model
exactly had to change
the difference between.
from the like line to the intersection of similarity. Interesting. I've heard that from the same book. I've been people, I've thought that I didn't realize that was the gap.
SLT should spot it says this noise is.
Yeah.
Which is probably reveals structure.
Yeah, that sounds right.
Yeah.
Nobody's put that together.
Like, do you think that makes the justice? I'm imagining you're hitting the lobster.
I see.
Yeah.
Okay. The reason
Yeah.
why it seems like something interesting that there is.
So where do you see the
Yeah,
jump?
but I guess there's like a, I know there's like basically like at least one paper I know that like uses like literally the projection as a point and like finds like a lot of these inductive biases are like still conserved without, you know, entity, so it seems like maybe it's the cluster, but it's like a secondary.
Okay, go.
Yeah, but not for like. It seems at least for there, like some multiple models where like the inductive biases you get from SGD are the same as the ones you get from projection sampling. Something like that. Yeah, so that's just like volume in those spaces like important predictions. Yeah, you just randomly sample the aggregate and losses and then reject it. Yeah. So it's zero in order.
In between of the two things you said there, SJD, but the noise. Yeah.
so the in between would be
In between that
is
you
SGDLT.
expect the difference between JD plus noise and SJD plus noise.
Yeah.
I feel like it should be emphasized more that SLT holds in the GD plus noise case, because I feel like there are a lot of like science and deep learning people who
So-
like there's not much gap there.
That's kind of what I'm getting at, because like the difference between GD and SJD is that you can scale SJD because you're taking a random sample of gradients, whereas like GD.
Well, there is difference between STD and impeding fist noise, which Dan was getting at, which is that there's like actual information in like, but one example actually, one concrete example is sparse parity is learnable by STD, but not by PD with noise.
We are overseeing.
And it's because you can like sort of by only presenting a few samples at a time.
Can escape.
Learn information that it couldn't learn from batch samples all presented at once. The fact that there's a small batch of samples gives you
Right.
information.
Right. Is that related to sort of data distribution where like only, I'm guessing that the effect might come from the fact that the thing that you want to learn is actually represented in the tail end of your data distribution. And so you're relying on getting a batch, small batch of them that.
Yeah.
Otherwise that would be drawn, like for example, if it is
Yeah,
I'm thinking of power laws.
Yeah, although well, there was one. Sorry, I said sparse parity. It's the particular parity is learnable by STD, but not Judy with noise. Sparse, but the sparse parity is like something. But it's particular, which means that the like classical like SQ learning or whatever model for like statistical query learning, like says that parity learning is impossible, but actually SGD is technically possible, although I don't think this actually really works like empirically. It's like a very small, like, yeah.
Yeah.
Pushing it towards more.
Could you tag?
Yeah, yes. Well, I'll have to go and find this again. But
Okay.
yeah, okay. I'm only seeing it for everyone.
Yeah. Okay. Yeah. Yes.
So that you end up with this model. You said that there would be